In this video, we'll be talking about complex conjugates. So by definition, we say that a pair of complex numbers, a plus bi and a minus bi, are complex conjugates. This is very similar to how we've talked about conjugates in the past. Namely, if you have an addition of two things, its conjugate is its subtraction. If you have a subtraction of two things, its conjugate is the addition. You just change the sign between the two. Also, as we saw in the last section, multiplying such a pair always gives a real number. Namely, a plus bi times a minus bi would give us first, outer, inner, last. But here, the middle terms cancel, and the I squared becomes a -1, so that gives us a squared plus b squared. In other words, multiplying a complex number by its complex conjugate always will give you just the square of the real part plus the square of the imaginary part put together, okay? We could use this formula in general. However, far more interesting is to just go through and do it out each time. So let's go through and do this. So for instance, we can multiply this by its complex conjugate, which would be 1 minus I. Doing that, again, we get a difference of squares. We'd have 1 squared minus I squared. We'll write it that way. But that's 1 plus 1, which is 2. Here, its conjugate would be 4 plus 3i, and that would give us 4 squared minus 3 squared I squared, but again, that gives me 4 squared plus 3 squared, which is 16 plus 9. 16 and 9 give me 25. And now it's time to have you try an example, so go ahead and multiply each of the following complex numbers by its complex conjugate and simplify down to standard form. On the count of, well, to the real number. On the count of 3, I'll reveal the solution. 1, 2, 3. So again, these are similar to the last example I worked. So, moving on, for example, we actually get a way to do division now as well. And the way we're going to do division is, to divide, we're going to multiply the bottom, the top and bottom, by the conjugate of the bottom. Namely, 4 plus 2i, 4 plus 2i. And the reason we do this is because then the bottom will become a real number. Whereas the top, we can just FOIL out. Foiling out the top, we have 8 plus first, outer, inner, last. Okay. On the bottom, we get 4 squared minus 2 squared I squared, our usual difference of squares, as we saw in the last two examples. And then what do we have? Well, combining like terms, this would be minus 6. So we have 8, 4i is 16i, and then minus 6 on top. That was in the last video. On the bottom, we have 4 squared plus 4 squared. 16 plus 4, because the I squared is -1. And so we have 20 on the bottom. Whereas on the top, we have 8 minus 6. 8 minus 6 is 2. And then we have 16 plus 16i. But then we could break this up now. Since there's only one thing in the denominator, we can break this up. Get 2 over 20 plus 16 over 20i. That gives us 1/10 plus, reducing this down would be 4/5 I. And there we magically were able to divide the numbers. However, this should seem a little bit familiar, especially this step. Namely, this was exactly how we rationalized the denominator earlier, right? Namely, if we had some sort of a number, a real number, a rational number plus some root, some square root, we always multiply top and bottom by the conjugate to rationalize the denominator. That's essentially what we're doing here, except in this case, our irrational thing is a square root of -1, so it's not even a real number. And in fact, what we're doing is we're kind of getting rid of that and thus creating a real number by doing so. And now let's have you try an example. So go ahead and write 2i divided by 2 minus I in standard form using the example I just did earlier as a guide. On the count of 3, I'll reveal the solution. 1, 2, 3. So here, again, we multiply top and bottom by the conjugate of the bottom. Doing so, we create a difference of squares in the bottom, namely a real number. At the top, we just FOIL, simplifying both of them down gets us to this step, and then we go ahead and break up the numerator over the denominator, which we can do. And so we have 3/5 plus 4/5 over I. For more practice and working with complex conjugates and doing out and using them to do division, be sure to see page 150 of the textbook and work problems 6 and 39 through 58. In our next video, we'll talk about the real point of studying complex numbers for this class, which is as complex solutions to quadratic equations.